Size estimates depend on when you observe it. This behavior isn't fully understood theoretically. Models can reproduce some pulsation characteristics, but struggle with others. The fundamental driving mechanism likely involves opacity changes in the atmosphere. As temperature varies, the gas becomes more or less transparent to radiation, which affects how efficiently energy escapes, which feeds back into the temperature and pressure, creating oscillations. But the details get complicated quickly, especially when you factor in convection, rotation, and mass loss. Some researchers suggest that irregular pulsations might trigger enhanced mass loss episodes. A particularly strong pulsation could temporarily increase the atmosphere's size and decrease its density, making it easier for radiation pressure to push material beyond escape velocity. If this happens repeatedly, the cumulative effect could strip away significant mass over relatively short timescales. Evidence for this comes from observations of circumstellar shells around some red supergiants, suggesting episodic rather than continuous mass loss. Stephenson 2-18 might be undergoing such episodes now. The high infrared excess indicates substantial dust in the surrounding envelope, consistent with recent or ongoing mass ejection. Whether this represents the star's normal state or a temporary phase remains unclear. Monitoring over years or decades would reveal trends, but funding for long-term observational programs is often difficult to secure when competing against newer, flashier projects. The broader question persists: how do stars this large form in the first place? Initial mass determines evolutionary path. Stars born with 8 solar masses or more will eventually explode as supernovae. Stars above perhaps 25 solar masses might collapse directly into black holes. But stars with initial masses of 30, 40, 50 solar masses or more face additional challenges during formation. Massive star formation happens in giant molecular clouds where gas densities are high. Gravity pulls material together, forming a protostellar core. As mass accumulates, the object heats up from gravitational compression. Eventually, temperature and pressure in the core become sufficient to ignite fusion. But for very massive stars, radiation pressure from fusion can halt further accretion before the star reaches its full potential mass. This creates a theoretical upper limit to stellar mass, somewhere around 150 to 200 solar masses for typical conditions. Stars more massive than that should blow themselves apart during formation. Yet observations occasionally reveal stars that seem to exceed this limit, suggesting either the limit is softer than theory predicts, or these objects formed through special circumstances, perhaps mergers of smaller stars, or unusually low metallicity environments where radiation pressure is less effective. Stephenson 2-18 likely started with initial mass in the 30 to 40 solar mass range, possibly higher. Over 17 million years, the cluster's estimated age, it evolved from a hot, compact main sequence star into the bloated red supergiant we observe today. The transformation required burning through its hydrogen fuel, expanding as core fusion shifted to heavier elements, shedding mass through stellar winds, all while convective mixing brought process material to the surface. Now it exists in a precarious state, balanced between fusion energy pushing outward and gravity pulling inward, slowly consuming whatever fuel remains accessible. The end comes when that balance breaks, when the core exhausts its nuclear options and collapses, triggering the supernova that will briefly outshine the entire galaxy before fading, leaving behind a neutron star or black hole. That dramatic finale raises another question. What actually triggers the supernova itself? Core collapse sounds straightforward, but the mechanism involves physics operating at extremes that still puzzle researchers. When fusion ceases, the iron core contracts rapidly under gravity. Electrons get squeezed into protons, forming neutrons and releasing neutrinos. Within a second, the core shrinks from roughly Earth's size to maybe 20 kilometers across. Densities reach levels comparable to atomic nuclei, unimaginable compression that creates a neutron star. The outer layers, no longer supported, plunge inward at significant fractions of light speed. They hit the newly formed neutron core and bounce. That rebound, combined with the enormous flux of neutrinos streaming outward, blows the star apart in a Type II supernova. At least that's the simplified version taught in introductory astronomy courses. Reality proves messier. Computer simulations of core collapse supernova struggled for years to produce explosions. Early models showed infalling material simply piling onto the proto-neutron star without rebounding strongly enough to reverse the collapse. Researchers kept refining their codes, adding better neutrino physics, improving resolution, incorporating magnetic fields and rotation. Modern simulations now successfully explode, but the process teeters on a knife edge. Small changes in initial conditions, slight differences in rotation rate, core structure, or neutrino opacity can mean the difference between a successful supernova and a failed one that forms a black hole directly without much visible display. Some massive stars might experience such failed supernova, collapsing quietly into darkness. We'd never know unless we happened to be monitoring that particular star at the time, noticing it suddenly disappeared from observations. Stephenson 218 will probably explode successfully given its mass and composition, but certainty remains elusive. The supernova itself will be spectacular, briefly radiating more energy than the entire cluster combined, visible across the galaxy despite 20,000 light-years distance. For a few weeks, it might even be visible to the naked eye from Earth, appearing as a moderately bright star in scutum before fading over months. The explosion will disperse much of the star's mass, enriching the interstellar medium with heavy elements forged during the star's lifetime and in the supernova itself. Elements heavier than iron form primarily in these explosive events, where neutron capture processes have time to build up atomic nuclei beyond what normal fusion allows. Gold, platinum, uranium, these owe their existence to supernovae and related cataclysms. The expanding debris will sweep through surrounding space, triggering shockwaves that compress nearby gas clouds, potentially inducing new star formation. The remnant at the center will be either a neutron star or a black hole, depending on how much mass falls back onto the core after the initial bounce. Neutron stars are bizarre objects in their own right, stellar corpses so dense that a teaspoon of their matter would weigh billions of tons on Earth. They can spin hundreds of times per second, generating powerful magnetic fields that channel radiation into beams, creating pulsars we detect as regular radio pulses, or they might be magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, occasionally releasing bursts of energy that briefly outshine the entire galaxy in gamma rays. If enough mass falls back, the neutron star crosses its stability limit and collapses further into a black hole, a region where gravity becomes so intense that not even light escapes. Black holes from stellar collapse typically range from a few solar masses up to perhaps 50 or 60, though recent gravitational wave detections hint at heavier ones forming through mergers. The black hole left by Stephenson 218 would likely fall in the 10 to 20 solar mass range, accounting for the mass lost through winds and the supernova ejection. Either outcome represents the final transformation, the ultimate endpoint of the stellar evolutionary sequence that began 17 million years ago, when a dense clump in a molecular cloud started collapsing under its own gravity. From protostar to main sequence star to red supergiant to supernova to neutron star or black hole. The journey spans millions of years, but the final collapse happens in seconds. That timescale contrast captures the dramatic nature of stellar evolution. Long periods of relative stability punctuated by rapid transformations. Our Sun will never experience such drama. It lacks the mass needed to become a supergiant or explode. Instead, in 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, possibly Earth too. Then it will shed its outer layers gently, forming a planetary nebula, while the core contracts into a white dwarf, a different kind of stellar remnant, supported not by fusion or neutron degeneracy pressure, but by electron degeneracy, the quantum mechanical resistance of electrons to being compressed. White dwarfs cool slowly over trillions of years, eventually fading to black dwarfs, though the universe hasn't existed long enough for any black dwarfs to form yet. They represent the future of most stars, quiet cooling rather than explosive demise. Only the massive stars, those born with 8 solar masses or more, die young and violently. They burn through their fuel quickly, shine brilliantly, and end catastrophically. Stephenson 218 exemplifies this pattern taken to an extreme. A star so massive it became enormous, so luminous it rivals small galaxies, so unstable it sheds mass continuously, and destined to explode with such force that the event will be visible across a significant fraction of the observable galaxy. The sheer scale challenges intuition. 2,000 times the Sun's rad. Ice means the volume exceeds 10 billion suns. If hollow, you could fit our entire inner solar system inside with room to spare. The surface area equals roughly 40 million times Earth's. Standing on a hypothetical planet orbiting at a safe distance, the star would span a substantial arc of the sky, glowing dull red, its limb darkening effect making the edges fade gradually into space. The view would be alien and unsettling, a bloated crimson orb dominating the heavens, slowly pulsating, occasionally ejecting clouds of gas that would glow as they caught stellar radiation. Any closer, and the tidal forces would tear planets apart. Any farther, and the light would dim too much to support conventional life. Not that life could exist near such a star anyway. The intense radiation, stellar winds, and short lifetime would preclude biological evolution. By the time multicellular life might develop, the star would already be dead. Life requires stable, long-lived stars like our Sun. Middle-aged, unremarkable yellow dwarfs that burn steadily for billions of years. Massive stars are the universe's fireworks, spectacular but brief, yet they play crucial roles in cosmic ecology. Their deaths distribute heavy elements necessary for planet formation and life. Without generations of massive stars living and dying, enriching the interstellar medium, the universe would remain mostly hydrogen and helium. No carbon for organic chemistry, no oxygen for water, no silicon for rocks, no iron for planetary cores. Earth itself is built from the ashes of dead stars, many of them likely red supergiants that exploded as supernovae billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged inside massive stars and scattered through space when they died. This connection makes stellar evolution deeply personal. We are literally made of stardust, descendants of stellar nucleosynthesis. Stephenson 218, when it eventually explodes, will contribute to future generations of planets and potentially future life forms that won't exist for billions of years. The atoms currently swirling in its envelope might one day be part of a distant world's ocean or a future being's body. That continuity, matter recycling through cosmic timescales, connects everything across space and time. How many stars like Stephenson 2-18 exist in the galaxy? Red supergiants are uncommon, but not exceptionally rare. The Milky Way probably hosts thousands at any given time, though most are too distant or obscured to detect easily. Each represents a massive star in late evolutionary stages, destined to explode within the next few million years. Some are even larger than Stephenson 2-18, though measurement uncertainties make definitive rankings difficult. Others are smaller, but still enormous by normal standards. Together, they form a population of dying giants scattered throughout the galactic disk. Their distribution isn't random. Massive stars form in clusters, born from the same molecular cloud. They tend to remain relatively close to their birthplace, though over time, gravitational interactions and galactic rotation disperse them. Stephenson 2 cluster contains multiple red supergiants, suggesting a burst of star formation 17 million years ago that produced several massive stars now reaching the end of their lives. In a few million years, they'll explode sequentially, each supernova potentially triggering more star formation in nearby clouds, seeding the next generation. This cycle has repeated countless times since the galaxy formed over 13 billion years ago. Early generations of stars were metal poor, containing only hydrogen and helium from the Big Bang. They lived and died, enriching the interstellar medium. Subsequent generations incorporated those heavy elements, allowing rocky planets and eventually life. We exist in an era where multiple generations of stellar evolution have built up substantial metallicity. Future stars will be even more metal-rich, assuming star formation continues long enough. But the universe's expansion and the gradual consumption of gas into stars and stellar REM means star formation will eventually cease. In 1 trillion years, the last stars will be dying and the universe will enter a dark era dominated by stellar remnants. Stephenson 2-18's explosion will occur long before then, but it's part of the same grand narrative. The universe's ongoing evolution from the hot, dense state of the Big Bang toward the cold, diffuse future where stars no longer shine. That cosmological perspective contextualizes individual stars. Each one, no matter how spectacular, is a temporary structure, an eddy in the cosmic flow, existing briefly before dissolving back into the substrate. Stephenson 2-18 may be the largest star we currently know, but it's still finite and mortal. In cosmic terms, its entire lifetime, from formation to supernova, represents a mere eye blink. The universe was ancient before Stephenson 2-18 formed. It will continue for eons after its remnant cools to invisibility. This humbling scale makes astronomy both awe-inspiring and sobering. We observe these magnificent objects, calculate their properties, marvel at their extremes, but they're ultimately transient, as are we. The difference is one of degree, not kind. Humans live decades. Stars live millions or billions of years. Galaxies persist for tens of billions. But all are temporary patterns in space-time, arising from the interplay of fundamental forces, destined eventually to dissipate. Does that diminish their significance? Perhaps it enhances it. Stephenson 2-18 exists now, shining brilliantly despite its inevitable doom. We exist now, able to observe and understand it despite our brief lifespans. The fact that both are temporary doesn't make them meaningless. It makes them precious. These moments of existence, whether stellar or human, are the universe's opportunity to experience complexity, to generate structure and beauty from simple physical laws. When Stephenson 2-18 explodes, it will create a spectacle that, while violent, is also creative, dispersing materials that will build future worlds. That's not tragedy, that's transformation. The atoms that comprise the star won't vanish. They'll scatter, cool, mix with interstellar gas, eventually get swept into new star-forming regions, become part of new stars and planets. Some might even participate in new forms of life, if conditions allow. The cycle continues, powered by gravity, fusion, and the fundamental laws of physics, unfolding across timescales that dwarf human comprehension, but remain understandable through careful observation and mathematical reasoning. That understanding represents one of humanity's greatest achievements. A few centuries ago, stars were mysterious lights of unknown nature. Now, we can analyze their composition from hundreds or thousands of light years away, model their interiors, predict their fates. We've discovered that the largest stars are thousands of times bigger than our Sun, that they burn through their fuel rapidly, that they'll die spectacularly. We know Stephenson 218's temperature, luminosity, mass loss rate. We understand the nuclear reactions powering it, the physics governing its structure, the evolutionary path that brought it to its current state. This knowledge didn't come easily. It required generations of astronomers building better instruments, developing theoretical frameworks, testing predictions against observations. It required physicists unraveling nuclear physics, understanding quantum mechanics, solving the equations of stellar structure. It required international collaboration, sharing data and ideas across borders and decades. The result is a coherent picture of stellar evolution that explains countless observations and makes testable predictions. That picture still has gaps and uncertainties, especially regarding the most extreme objects, but it's remarkably successful for something as complex as stars. Stephenson 218 fits within this framework, though it pushes the boundaries. Its extreme size and high mass loss rate challenge models. Its variability and infrared excess suggest complex atmospheric dynamics we're still working to understand fully. But none of this contradicts our basic understanding of how massive stars evolve. It just shows that nature explores the full parameter space available, producing objects at the edge of what's possible. Studying these extremes helps refine our theories, exposing weaknesses and prompting improvements. Every anomaly is an opportunity to learn something new. That process of discovery and verification continues. New telescopes with better resolution probe deeper into obscured regions. Improved distance measurements from spacecraft like Gaia refine our estimates. Computer models grow more sophisticated, incorporating additional physics. Each advance brings sharper focus, but also reveals new complexities we hadn't anticipated. Consider the measurement challenges. Stephenson 218 sits embedded in dense dust clouds that absorb most visible light. Only infrared radiation escapes, carrying information about the star's properties. But dust complicates interpretation. It absorbs some wavelengths preferentially, distorting the spectrum. It re-radiates energy at cooler temperatures, adding infrared excess. Disentangling the star's actual emission from these effects requires careful modeling and multiple observations at different wavelengths. Distance uncertainty compounds the problem. The star lies roughly 20,000 light-years away, but that figure has substantial error bars, potentially 50% or more. When you're trying to determine a star's physical size, distance matters enormously. Brightness decreases with the square of distance, so an object twice as far is 4 times dimmer. If our distance estimate is wrong, our luminosity calculation will be wrong. And luminosity connects directly to size through the Stefan-Boltzmann law, meaning distance errors propagate through every derived property. This isn't unique to Stephenson 2-18. Most record holder candidates face similar issues. UY-Scooty's size estimates have been revised significantly as better data became available. What was once thought to be 1,700 solar radii dropped to around 900 in more recent analyses using improved distance measurements from Gaia. That's still enormous, but nearly half the original estimate. Such revisions happen regularly in astronomy as techniques improve and new data arrives. Does that make the earlier measurements wrong? Not exactly. They were the best estimates possible with available information. Science progresses through refinement, not by achieving perfection on the first try. Each generation of instruments and methods improves accuracy, narrowing uncertainty ranges, revealing details previously hidden. Today's measurements will likely be revised by future observations, with instruments we haven't built yet. That's expected and healthy. What remains constant is the existence of these extreme objects, pushing stellar physics to its limits. Whether Stephenson 218's radius is 2,150, or 1,800 or 2,000 solar radii doesn't fundamentally change its nature as an extraordinarily large, unstable star nearing the end of its life. The exact number matters for detailed modeling, but the broader picture stays consistent. Massive stars evolve rapidly, expand enormously, lose mass prodigiously, then explode. The specifics vary, but the overall pattern holds. That pattern reveals something fundamental about stellar physics. There are limits to how large stars can grow, set by the balance between gravity and radiation pressure. When a star's luminosity becomes high enough, radiation pressure on its outer layers can exceed gravitational binding. Material gets blown away, carrying mass from the star. This mass loss accelerates as stars become more luminous and extended, creating a natural ceiling on stellar size. Stephenson 218 appears to be testing that ceiling. Its high mass loss rate, evidenced by strong infrared excess and MESA emissions, suggests material streaming away constantly. The star is gradually destroying itself, shedding outer layers that will never collapse inward during the eventual supernova. This pre-explosion mass loss affects the final fate significantly. Less mass at core collapse means different explosion dynamics, different remnant properties, different chemical yields. Understanding these processes requires combining observations with theoretical models. We can't watch a single star complete its evolution. That takes millions of years. But we can observe many stars at different evolutionary stages, building a composite picture. Stephenson 2-18 represents one data point in that picture, an example of extreme red supergiant evolution captured at a particular moment. Other stars in the Stephenson 2 cluster provide additional data points, all at roughly the same age, but with different initial masses and therefore different evolutionary states. The cluster context matters. Stars in Stephenson 2 formed together about 17 million years ago from the same giant molecular cloud. They share similar chemical composition and age, but differ in initial mass. The most massive have already evolved into red supergiants, while less massive ones remain on the main sequence. By studying the full population, astronomers can test evolutionary models against real data. Does the predicted progression from main sequence to red supergiant to supernova match what we observe? Mostly yes, though with details requiring adjustment. Stephenson 218 itself shows features suggesting complex atmospheric dynamics. Variable stars like this undergo periodic expansions and contractions, driven by instabilities in their outer layers. Material heats, expands, cools, falls back, creating pulsations with timescales of months or years. These pulsations can be violent enough to temporarily distort the star's shape and eject material episodically. The infrared excess observed around Stephenson 2-18 might result from dust condensing in these ejected shells, forming a dusty envelope around the star. Such envelopes aren't unusual for red supergiants. Many are surrounded by extensive circumstellar matter created by ongoing mass loss. This material obscures the central star, making direct observation difficult. It also creates an extended atmosphere where chemistry happens. Molecules and dust grains form in the cooler outer regions, then get swept away by stellar winds or radiation pressure. The result is a complex, dynamic environment, quite different from the relatively simple photosphere of a main sequence star. Studying this environment requires multiple techniques. Infrared imaging reveals the spatial distribution of dust. Spectroscopy identifies molecules through their characteristic absorption or emission lines. Interferometry measures angular sizes with high precision, resolving details impossible with single telescopes. Maser emissions trace specific physical conditions in the circumstellar gas. Each technique provides different information, and combining them creates a comprehensive picture. That picture shows Stephenson 218 as an active, evolving system. The star isn't static, it's constantly changing, though on timescales longer than human observation periods. Material flows outward, carrying away mass and energy. The stellar radius fluctuates as pulsations expand and contract the outer layers. Dust forms and dissipates in the surrounding envelope. All these processes interconnect, driven by the enormous energy output from fusion happening deep in the core. Which brings us back to fundamentals. Everything we observe at the surface traces back to nuclear physics in the interior. Fusion reactions generate energy, creating pressure that supports the star against collapse. But fusion rates depend on temperature and composition. As helium builds up in the core, fusion shifts to heavier elements. Carbon burning, oxygen burning, each stage proceeding faster and at higher temperatures. The star's structure adjusts continuously in response. For extremely massive stars like Stephenson 2-18, this evolution happens remarkably quickly. A star with 25 solar masses might spend only a few million years as a red supergiant before exploding. That's a blink compared to the Sun's 10 billion-year lifetime. The rapid pace reflects higher core temperatures, enabling faster fusion rates. More luminosity means more fuel consumption. The candle that burns twice as bright burns half as long, except here, the ratio is far more extreme. During its red supergiant phase, the star experiences repeated cycles of expansion and contraction, sometimes ejecting significant mass in the process. These episodes might create multiple shells of circumstellar material, each representing a distinct mass loss event. Observing these shells provides clues about the star's recent history and future evolution. Did it experience a particularly violent ejection recently? Are the mass loss rates increasing as the star approaches instability? The answers have implications beyond this single object. If we understand how the most massive stars lose mass, we can predict their final fates more accurately. That matters for understanding supernova rates, neutron star and black hole formation, chemical enrichment of galaxies. Massive stars are rare, but they dominate certain astronomical processes due to their extreme properties. They inject energy into their surroundings through stellar winds and supernova explosions. They create and disperse heavy elements essential for planets and life. They shape the interstellar medium, triggering new star formation while simultaneously disrupting nearby clouds. Stephenson 2-18 will contribute to all these processes when it explodes. The exact nature of that explosion depends on details we're still working to understand. Will it be a standard core collapse supernova? A more energetic hypernova? Could it collapse directly to a black hole without a bright explosion? The answers depend on the remaining core mass, rotation rate, and magnetic field strength. Quantities difficult to measure directly. What we can measure is the current state. The star's luminosity, temperature, mass loss rate, variability characteristics. These observables constrain models of the interior structure and evolutionary state. They tell us the star has progressed well beyond hydrogen burning, likely fusing heavier elements in its core now. They suggest instabilities that will intensify as fusion progresses through increasingly unstable nuclear regimes. They point toward an endpoint approaching within the next few million years, possibly sooner. That endpoint represents a transition from one type of astronomical object to another. the star will cease being a star in any conventional sense. Its core will collapse in seconds, releasing more energy than the sun will emit in its entire lifetime. The outer layers will be blown away, creating an expanding remnant that will remain visible for tens of thousands of years. At the center, either a neutron star or black hole will form, depending on how much mass falls back onto the collapsing core. Either outcome represents an extreme physical regime. Neutron stars pack more than a solar mass into a sphere only kilometers across, creating densities comparable to atomic nuclei. Black holes take this further, compressing matter to infinite density according to general relativity, creating space-time curvature so extreme that not even light escapes. Both represent the ultimate fate of matter pushed to gravitational collapse, preserved only by exotic physics that barely functions under such conditions. Stephenson 2-18's ultimate remnant type remains uncertain. It depends on processes happening now in the invisible core, processes we infer from surface observations and theoretical models. But regardless of details, the star exemplifies a fundamental cosmic cycle. Matter assembled into a massive star. Fusion converted light elements into heavy ones while releasing energy. That energy supported the star temporarily against gravity's inexorable pull. Eventually, fuel exhaustion allows collapse, triggering an explosion that disperses processed material back into space. The cycle completes, ready to begin again when that dispersed material collapses into new stars. This cycle has operated for billions of years, gradually enriching the universe with heavy elements. The first stars contained only hydrogen and helium from the Big Bang. When they exploded, they seeded their surroundings with carbon, oxygen, silicon, iron, elements forged in their cores and during the supernova itself. Subsequent generations of stars incorporated these elements, creating even more complex chemistry. By now, after countless stellar generations, the interstellar medium contains a full periodic table of elements, all created through nuclear fusion and supernova nucleosynthesis. Stephenson 2-18 participates in this ongoing process. It's creating elements now through fusion in its core. When it explodes, it will scatter those elements across light years of space. Some will eventually become part of new stars, new planets, possibly new forms of life. The atoms comprising your body originated in similar processes billions of years ago, in stars whose names we'll never know. You're made of stellar debris, recycled matter from ancient supernovae, temporarily organized into a conscious being capable of contemplating its own origins. That's perhaps the most profound connection between human existence and extreme stars like Stephenson 2-18. We're not separate from these cosmic processes, we're products of them. Every element heavier than helium in your body came from a star. The calcium in your bones, the iron in your blood, the carbon forming your cells, all forged in stellar cores or supernova explosions. We are quite literally made of star stuff, as Carl Sagan memorably observed. Understanding this connection transforms how we view both ourselves and the universe. We're not isolated observers watching distant phenomena unrelated to our existence. We're participants in cosmic evolution, temporary arrangements of matter that arose because earlier stars lived and died, creating the chemical complexity necessary for life. Stephenson 2-18 represents one link in that chain, a current example of processes that have operated throughout cosmic history. When this star explodes, it will create new elements and disperse them widely. Those elements might someday participate in new planetary systems, possibly hosting their own forms of life. Those hypothetical future beings might look up at their night sky and observe even larger stars, perhaps wondering about their own cosmic origins, just as we do. The cycle continues. Consciousness emerging repeatedly from matter, organized by physical laws, acting over vast timescales. This perspective shift changes everything about how we observe distant stars. When you look at Stephenson 218, you're not viewing an isolated object. You're witnessing a moment in an eternal process that connects past, present, and future across cosmic timescales. The star exists now in a specific evolutionary state, but that state resulted from conditions set billions of years earlier when the galaxy was younger and different. The materials forming Stephenson 218 came from previous stellar generations. Those earlier stars created heavy elements through fusion, then dispersed them via supernovae. Gas clouds enriched with these elements eventually collapsed under gravity, forming new stars including the Stephenson 2 cluster. This recycling process has operated continuously since the first stars formed roughly 13 billion years ago. Each generation adds complexity to the cosmic chemical inventory. First-generation stars contained only primordial hydrogen and helium. They couldn't form planets because rocky worlds require heavier elements. When these population 3 stars exploded, they seeded space with carbon, oxygen, magnesium, silicon, iron. Second-generation stars incorporated these elements, creating even more through their own fusion processes. By now, after countless cycles, interstellar gas contains every naturally occurring element in the periodic table. Stephenson 218 formed from such enriched material, though its exact composition remains somewhat uncertain due to observational limitations. The enrichment process operates at different rates in different galactic regions. The Milky Way's central regions experience more star formation historically, leading to higher metal content in stars forming there today. Stephenson 218, located roughly 20,000 light-years from Earth near the galactic center, formed in a relatively enriched environment. This metallicity influences stellar evolution in subtle ways, affecting opacity in stellar atmospheres, wind-driven mass loss rates, and internal convection patterns. Higher metallicity generally promotes greater mass loss, which might partially explain why Stephenson 218 sheds material so rapidly despite its young age. Understanding this star requires considering multiple interacting factors simultaneously. Surface temperature determines photon wavelengths emitted. Luminosity indicates total energy output. Mass loss rate affects long-term evolution. Internal structure governs stability. Each factor connects to others through physics. Higher luminosity drives stronger radiation pressure, increasing mass loss. Greater mass loss reduces total stellar mass, affecting gravitational compression in the core. Changed core conditions alter fusion rates, modifying energy generation. It's a complex system where changing one parameter cascades through the entire structure. Astronomers construct computer models attempting to capture these interactions mathematically. Modern stellar evolution codes incorporate detailed physics, including nuclear reaction networks, radiation transport, convection modeling, mass loss prescriptions, and rotation effects. Researchers input initial conditions, mass, composition, rotation rate, then let equations predict how the star evolves over millions of years. These models successfully reproduce many observed stellar properties, lending confidence to predictions about stars like Stephenson 2-18. Yet models contain uncertainties. Some physical processes remain incompletely understood, requiring approximations. Convection, the transport of energy via gas circulation, follows complex turbulent flows difficult to model precisely. Mass loss mechanisms, especially for extreme stars like hypergiants, involve intricate physics that current theories capture only approximately. Small uncertainties in these processes compound over evolutionary timescales, creating larger uncertainties in long-term predictions. This explains why astronomers can't definitively state whether Stephenson 2-18 will explode in 10,000 years or 100,000 years. The star's current state seems clear: massive, luminous, evolved, unstable. Its eventual fate seems inevitable: supernova explosion, probably leaving a black hole remnant. But the precise timeline depends on details like current core mass, ongoing mass loss rates, and internal mixing processes, all of which carry significant uncertainties. Observational limitations compound these theoretical uncertainties, making precise predictions impossible with current data. Future observations might narrow these uncertainties. Next-generation telescopes with improved infrared capabilities could penetrate the dust surrounding Stephenson 2-18 more effectively, revealing surface details currently obscured. Interferometry techniques continue advancing, potentially enabling direct measurement of the star's diameter with better precision. Long-term monitoring programs, tracking brightness variations and spectral changes, could constrain models by providing detailed evolutionary data. Each observational improvement refines our understanding incrementally. Meanwhile, theoretical work continues advancing. Improved computational power enables more sophisticated simulations, incorporating finer physical detail. Laboratory experiments and quantum calculations provide better nuclear reaction rates for stellar conditions. Observations of other massive stars in various evolutionary stages inform general understanding applicable to Stephenson 2-18. Gradually, piece by piece, the picture becomes clearer, even if complete certainty remains elusive. This ongoing scientific process mirrors how knowledge advances generally. Initial observations reveal phenomena demanding explanation. Preliminary theories emerge, making testable predictions. Further observations refine or contradict those predictions. Theories adapt, becoming more sophisticated and accurate. The cycle repeats indefinitely, each iteration bringing deeper understanding without ever reaching final complete knowledge. Stephenson 2-18 exemplifies this process perfectly. We know vastly more about it now than when first catalogued, yet fundamental questions persist. What makes this particular star scientifically valuable? Its extreme nature pushes stellar physics to boundary conditions. Normal stars follow well-understood evolutionary paths. Extreme stars test whether our theories work in regimes far from typical conditions. When models successfully predict hypergiant properties, that validates the underlying physics powerfully. When observations disagree with predictions, that reveals gaps in current understanding, pointing toward new physics requiring discovery. Stephenson 2-18 also provides a nearby example, cosmically speaking, of physical processes occurring throughout the universe. Similar massive stars exist in distant galaxies, millions or billions of light years away. We can't study those stars in detail due to their remoteness. But by thoroughly understanding Stephenson 2-18 and other nearby massive stars, we develop principles applicable universally. This local knowledge becomes a foundation for understanding stellar populations across cosmic distances and times. The star's connection to broader astrophysical questions extends further. Massive star explosions influence galactic chemical evolution, as discussed earlier. They also affect star formation rates in their neighborhoods. Supernova shockwaves compress nearby gas clouds, potentially triggering new star formation. Simultaneously, those shockwaves disperse and heat gas, potentially suppressing star formation in other regions. The balance between these effects shapes galactic structure and evolution over billions of years. Additionally, supernova from stars like Stephenson 2-18 might produce gravitational wave signals detectable by current or future instruments. If the core collapse proceeds asymmetrically, it generates gravitational radiation, ripples in spacetime itself, propagating outward at light speed. Current gravitational wave detectors have observed signals from merging black holes and neutron stars. A nearby supernova might produce detectable signals from core collapse, providing unprecedented data about processes occurring deep inside the exploding star. Such observations would constitute entirely new ways of studying stellar deaths. Light tells us about surface and atmospheric conditions. Neutrinos, if detected, provide information about core nuclear processes. Gravitational waves would reveal information about mass motions and asymmetries during collapse itself. Combining multiple observation types creates a comprehensive picture impossible to obtain from any single method alone. This multi-messenger astronomy represents the frontier of astrophysical research. The field has moved beyond simply observing light across various wavelengths. Now we detect particles, neutrinos, cosmic rays, and gravitational waves, all carrying complementary information about cosmic events. Future supernova observations, potentially including one from Stephenson, 2-18 if it explodes soon enough, will exploit all available channels simultaneously, revolutionizing our understanding of stellar deaths. The timeline remains uncertain though. Soon, in astronomical terms, might mean thousands of years. From a human perspective, Stephenson 2-18 could maintain its current state for many generations before finally collapsing, or it might explode tomorrow. The uncertainty frustrates efforts to predict specific events, but underscores how stellar evolution timescales vastly exceed human ones. We observe snapshots of processes unfolding over millions of years, making real-time evolution invisible except for the most rapid changes. This temporal disconnect between human and stellar timescales creates interesting challenges for astronomy. We can't watch individual stars evolve from birth to death. Instead, we observe many stars at different evolutionary stages, then construct theories connecting those snapshots into coherent evolutionary sequences. It's like trying to understand human aging by looking at photographs of different people at various ages, without ever watching anyone actually age. The approach works remarkably well, validated by consistency across many observations, but it lacks the certainty of direct longitudinal observation. Stephenson 2-18 will eventually provide one data point in that evolutionary sequence. When it explodes, astronomers worldwide will immediately observe the event across all available wavelengths and channels. That observation will test predictions about massive star deaths, supernova mechanisms, nucleosynthesis, remnant formation, and galactic feedback. A single well-observed supernova provides invaluable data constraining multiple theoretical areas simultaneously. Until then, the star continues its slow march toward instability. Fusion proceeds in the core, creating ever heavier elements. The outer envelope expands and contracts according to internal dynamics we only partially understand. Mass streams away steadily, carrying material back into interstellar space. And somewhere, hidden deep within, a growing iron core accumulates inexorably toward the critical mass where collapse becomes inevitable. That moment approaches, whether in years or millennia we cannot say. When collapse finally occurs, the event will be spectacular, even at 20,000 light-years distance. For weeks or months, the supernova might outshine the entire Milky Way, becoming potentially visible in daylight, depending on exact circumstances. The explosion will create a nebula visible for thousands of years afterward, possibly rivaling famous remnants like the Crab Nebula in complexity and beauty. And at the center, a black hole will remain, forever marking where once the largest known star existed. That future black hole will itself become an object of study. Its mass will encode information about the progenitor star's properties. Its spin will reveal details about angular momentum transfer during collapse. If it receives a velocity kick from asymmetric explosion, its motion through space will tell us about explosion dynamics. Even after the visible supernova fades, the remnant continues providing scientific value indefinitely. This represents the ultimate legacy of Stephenson 218. Long after human civilization potentially ends, long after Earth itself becomes uninhabitable billions of years hence, when our sun expands into a red giant, the black hole created by Stephenson 218's collapse will persist. It will orbit the galaxy eternally, occasionally encountering other objects, slowly evaporating via Hawking radiation over timescales that make the current age of the universe seem infinitesimal. The star's existence, however brief on cosmic scales, leaves a permanent mark on space-time itself. Perhaps that's the deepest lesson from studying extreme stars. They demonstrate how temporary structures can emerge from chaos, persist briefly, then dissolve back into the cosmos while leaving permanent traces. Stephenson 218 assembled from gas clouds that once belonged to other stars. It will disperse back into space, its material eventually forming new stars, planets, possibly life. But the black hole remains, and the heavy elements created persist indefinitely, incorporated into later cosmic structures. You participate in the same process. The atoms comprising your body came from stellar deaths billions of years ago. They've cycled through various forms: gas, dust, rock, biological molecules, before temporarily assembling into you. Eventually, they'll disperse again, recycling into new forms over timescales beyond imagining. The universe wastes nothing. Every atom gets reused endlessly, creating structures of ever-increasing complexity as cosmic evolution proceeds. Stephenson 2-18 represents one grand chapter in that eternal story, a chapter now approaching its dramatic conclusion before the cycle begins anew. Looking at Stephenson 2-18 from 20,000 light-years away, we're witnessing something that shouldn't exist according to our simplest models, yet clearly does. A star so massive, so extended, so unstable that it challenges every assumption about stellar limits. And that's exactly why it matters. The measurement uncertainties remain frustrating. Is the radius precisely 2,150 solar radii, or closer to 1,800? Different studies yield different answers depending on assumptions about distance, temperature, dust composition. Future observations with better instruments will refine these numbers, possibly crowning a different champion. NML Cygni might reclaim the title. Some undiscovered giant lurking in a heavily obscured region might surpass them all. But here's what the debate over exact measurements misses. The existence of these objects fundamentally matters more than their precise ranking. Whether Stephenson 218 is the absolute largest, or merely among the largest, doesn't change its significance. It represents stellar evolution pushed to extremes we're still learning to understand. It demonstrates that nature explores every possibility physics allows, creating structures at the edge of stability. These extreme stars serve as laboratories testing our theories under conditions impossible to replicate anywhere else. The temperatures, pressures, and densities in Stephenson 218's interior exceed anything achievable in terrestrial experiments. The mass loss rates, luminosities, and evolutionary timescales challenge our models in ways normal stars don't. Every observation adds constraints to theory. Every refined measurement narrows uncertainties. The star will explode eventually, maybe in 1,000 years, maybe in 100,000. The timeline remains uncertain, but the outcome seems inevitable. When collapse finally occurs, the supernova will briefly outshine billions of normal stars, visible across much of the galaxy despite the intervening dust. Astronomers will observe it with instruments far more sophisticated than those available today, capturing data that current researchers can only dream about. That observation will answer questions we haven't yet learned to ask. Until then, Stephenson 218 continues existing in its precarious state, fusing heavy elements in its core, shedding mass through powerful winds, pulsating according to internal dynamics we're still working to understand. It's simultaneously creating and destroying itself, building heavy elements through fusion while stripping away its outer layers through mass loss. The competition between these processes determines how much longer the star persists and what kind of remnant it ultimately leaves behind. The broader context matters more than any individual object. Stephenson 2-18 exists within a cluster of red supergiants, all roughly the same age, all approaching the ends of their brief lives. Within the next few million years, that cluster will experience multiple supernovae as its most massive members explode sequentially. Those explosions will enrich the surrounding interstellar medium with heavy elements, while simultaneously triggering new star formation through shock compression of nearby gas clouds. This cycle has operated since the first stars formed over 13 billion years ago. Each generation creates heavy elements through fusion and distributes them via supernovae. Subsequent generations incorporate those elements, enabling progressively more complex chemistry. Rocky planets became possible only after multiple stellar generations had enriched the interstellar medium with silicon, iron, magnesium. Life emerged only after billions of years of chemical enrichment provided the necessary elements: carbon, nitrogen, oxygen, phosphorus. You exist because stars like Stephenson 2-18 lived and died billions of years ago, creating the elements now comprising your body. The calcium in your bones came from stellar nucleosynthesis. The iron in your blood was forged in some ancient supernova. The oxygen you're breathing right now was created through fusion in a massive star's core, before being scattered by its explosive death. This connection transforms how we view both ourselves and the cosmos. We're not separate observers studying distant objects unrelated to our existence. We're participants in cosmic evolution, temporary arrangements of stellar debris, organized into conscious beings capable of understanding our own origins. The atoms making up your body have cycled through multiple stars over billions of years. They've existed as interstellar gas, as parts of ancient planets, as biological molecules in organisms that lived and died long before humans evolved. Stephenson 2-18 continues this process right now. It's creating elements through fusion that will eventually become part of future stars, planets, possibly future life forms. When it explodes, those newly created elements will scatter across light years of space, mixing with other material, eventually participating in new cosmic structures. The cycle never ends. Matter continuously recycles, creating increasingly complex arrangements as physical laws operate over vast timescales. The star's extreme properties reveal something fundamental about how the universe works. Physics allows certain maximum sizes for stars based on the balance between gravity pulling inward and radiation pressure pushing outward. Stephenson 2-18 appears to be testing that limit, existing in an unstable state where any perturbation might trigger catastrophic mass loss. The high infrared excess and strong MESA emissions indicate material streaming away constantly, suggesting the star is gradually destroying itself before the final collapse. Understanding these limits matters for cosmology. The first stars in the universe might have been even more massive than anything existing today because they formed from pristine hydrogen and helium, without heavy elements to facilitate cooling and fragmentation. Those hypothetical population 3 stars might have reached several hundred solar masses before exploding as pair instability supernovae. Events so energetic they completely destroy the star without leaving a remnant. We've never observed such explosions directly, but theory predicts they occurred in the early universe. Stephenson 2-18 helps us understand whether such extreme stars can exist by showing us what happens at the upper limits of stellar mass in our current epoch. If stars this size barely survive before tearing themselves apart through mass loss, that constrains how massive the first stars could have been. Each observation of extreme objects today informs our understanding of cosmic history. The quest to find the largest star will continue. New surveys will cover more of the galaxy with better sensitivity. Improved distance measurements will refine size estimates. Advanced modeling techniques will better account for dust, variability, and complex atmospheric effects. The title of largest known star will likely change hands multiple times as measurements improve and new candidates emerge from obscured regions. But that competition, while interesting, somewhat misses the point. These objects collectively reveal how stellar evolution works at extremes. They show us what happens when gravity, fusion, and radiation pressure compete in stars far more massive than our Sun. They demonstrate the chemical enrichment process that made planets and life possible. They provide natural laboratories where matter behaves under conditions we can never recreate artificially. Stephenson 2-18 represents one example among many, a particularly large example, possibly the largest currently known, but ultimately one member of a population of extreme stars scattered throughout the galaxy. Each contributes to our understanding. Each adds constraints to theoretical models. Each enriches the interstellar medium when it dies, seeding future star formation with heavy elements. The star's existence also reminds us how much remains unknown. Despite centuries of astronomical progress, we still can't precisely predict when individual stars will explode or exactly what processes trigger core collapse. We don't fully understand convection in massive stellar envelopes or what determines mass loss rates. We can't definitively say whether a given supergiant will leave behind a neutron star or black hole. These uncertainties don't represent failures of science. They reflect the genuine complexity of nature and the difficulty of studying objects at cosmic distances. Every answered question reveals new questions we hadn't known to ask. Every refined measurement exposes new puzzles requiring explanation. The process of discovery continues indefinitely, each generation building on previous work, while recognizing how much remains mysterious. Future astronomers will study Stephenson 2-18 with instruments we haven't invented yet, applying theoretical frameworks we haven't developed, asking questions we haven't conceived. They'll refine our measurements, correct our errors, and probably smile at how primitive our current understanding seems. That's how science progresses, not through achieving final complete truth, but through continuous refinement approaching closer to reality without ever fully arriving. And eventually, perhaps thousands of years from now, perhaps sooner, Stephenson 2-18 will explode. Those future astronomers will observe the supernova with technologies far beyond current capabilities, capturing data that will revolutionize understanding of stellar deaths. They'll detect neutrinos from the core collapse, gravitational waves from asymmetric mass motions, electromagnetic radiation across all wavelengths from radio to gamma rays. They'll watch in real time as shock waves tear through the stellar envelope, as heavy elements get synthesized in the explosion's heat, as a black hole forms at the center. The observation will answer questions while raising new ones, as all major discoveries do. But it will also represent a transition, the end of Stephenson 2-18 as a star, and its transformation into a supernova remnant. Then eventually just a black hole orbiting silently through the galaxy for eons to come. Until that moment arrives, the star continues its existence in our night sky, invisible to unaided vision, but blazing brilliantly in infrared wavelengths for those with instruments to detect it. It shines with the power of hundreds of thousands of suns, illuminating nothing but empty space around it, slowly dying while simultaneously creating the heavy elements that make complexity possible. Every second, fusion reactions in its core convert mass to energy according to Einstein's equation. Every second, stellar winds carry material away at hundreds of kilometers per second. Every second, the star inches closer to the moment when fusion can no longer support the weight of its own mass, and collapse becomes inevitable. That moment will come. The timeline remains uncertain, but the physics seems clear. And when it happens, when Stephenson 218 finally reaches the end of its brief, spectacular existence, it will create one of the most energetic events possible in the universe. A core collapse supernova that will briefly rival the combined light of 100 billion stars. But even in death, the star's atoms won't vanish. They'll scatter, disperse, mix with interstellar material, eventually collapse again under gravity to form new structures. The cycle continues, powered by the same fundamental forces that have shaped cosmic evolution since the Big Bang. Matter assembles, fuses, disperses, reassembles in endless repetition. Stars are born, live briefly or long depending on their mass, then die, sometimes quietly, sometimes explosively, always contributing their processed material back to the cosmos. This is the story of Stephenson 218, the largest star we currently know. A story that began 17 million years ago when a dense clump in a molecular cloud started collapsing. A story that will end in spectacular explosion within the next few million years at most. A story that's simultaneously unique and universal. One star among hundreds of billions in our galaxy alone, yet also an extreme example revealing fundamental truths about how stars work and how the universe evolves. The atoms comprising that star will persist long after the explosion fades. They'll become part of new stars, new planets, possibly new forms of life billions of years hence. Those hypothetical future beings might look up at their sky and wonder about their origins just as we do, never knowing that some of the atoms in their bodies came from a star called Stephenson 218 that exploded eons before their existence. And in that continuity, that endless recycling of matter through cosmic time, we find perhaps the deepest meaning. Nothing is permanent, but nothing is truly lost either. Everything changes form continuously while the underlying substance persists. Stars are temporary structures, as are planets, as are living beings. But the atoms endure, cycling through configurations of ever-increasing complexity as the universe's story unfolds.